In this video, we're going to continue our study of critical points, but we're going to look at classifying them based on formulas rather than contour diagrams. Remembering back to single variable functions, we had two tests. We had a first derivative test and a second derivative test. And remember, the first derivative test was the idea of positive slopes, and then a zero slope, and then a negative slope. That indicated the shape of the curve was laid out like this, and so you were at a local maximum. The second derivative test was about concavity, and that was about the bend of the function. If something was concave down at a critical point, then again, that would be a local maximum. It turns out, though, that only one of these extends nicely into multivariate calculus. The first derivative test in particular cannot be extended to multiple dimensions, at least not in any straightforward way. Now, why is that? Well, if we imagine a contour diagram where we're going up, up, and up, and then maybe we have a saddle point like so at height 0, and then maybe it goes up again. If we have that kind of configuration, and we ask ourselves, can I identify whether the function goes up, then levels off, then goes down? Well, the question is, in which direction? In a single variable function, there is only one direction, positive x. But if we're looking at a multivariate function, we can take a step into this peak from one direction, or this direction, or this direction. And how do we cover all of our bases? Especially if we contrast that with a critical point like a saddle point, where as we come in from this direction, we'd be going downhill and then uphill. Whereas if we go in the other direction, we're going uphill, then downhill. All of a sudden, the logic underpinning the first derivative test, the function increases, hits zero slope, then goes down, doesn't extrapolate to this new problem area where there are lots of different directions. In single variable, there's one direction, increasing x. In multivariate, there's an infinite number of directions, so no more first derivative test for us. Fortunately, we have the second derivative test that we can fall back on, and it does have a nice analog in multivariate calculus. Here's how it works. Imagine you're at a critical point. So again, we're always studying a point where the partial derivatives, the first partial derivatives, are equal to 0. We then look at the three shapes that we expect to get. These are the most common ways that we can get critical points. We have a local min, a local max, and our new point, the saddle. Now, what's interesting about those 3 points, or those 3 types of points, is the concavity. In this particular local minimum configuration, no matter where we look, we have concave up and nothing else. Well, concavity is all about the second derivative, and you'll see that our test is about the second derivative as well. If we contrast that with the local maximum, here we have all the directions being concave down. And then the mix one is the saddle point, where you have a mix of concave down and concave up, which we label a mix of concavities. So how do we actually test for those kinds of conditions based only on the formula? Well, here's the formula that is actually derived from a combination of calculus plus linear algebra. For those who have seen linear algebra and matrices, there's a nice tie-in here where we put the second derivatives into a matrix. And if you look at the calculation here, we're taking the x derivative times the y derivative. So it's the two concavities in the x and y directions respectively. And then we subtract this product here. And that is exactly what linear algebra would teach us is the determinant of this matrix. If you have not seen linear algebra, feel free to ignore that completely. This is just a nice mnemonic for those who have done some work with determinants and matrices. The way to think about it, though, is to focus on this main construction here. D is like the product of two concavities. There is this extra term at the end, and that accounts for the fact that not everything in the world lines up nicely along the x and y axes. So we have the mixed partial derivative here, the xy second derivative. But at the end of the day, the way we're going to reason about this second derivative test value is thinking about it as a combination or a product specifically of the two concavities. All right, minimum and maximum, these two cases here, both share d greater than 0. And if you think of d as being a product of concavities, then what this is telling us, if you have a product that's positive, is that both your multipliers are the same, have the same sign. Two concavities with the same sign. In other words, if you look at this, and then we extend it to looking at the x derivative, second derivative here being positive, what that translates to is two positive concavities. Let's approach this from the scenario here. If we have a local minimum, and there's two major directions where we see concave up, that would give us two positive second derivatives, well, one of them here, and the combined product of them being positive as well. That gets us back to a local minimum. If we're looking at a local maximum, what we see are two things that are concave down. So if we took the product, going back to here, if we took the product of those two negative concavities, that would turn into something positive overall, which is our d value. So d is positive, and one of the concavities is negative. It doesn't have to be this one, it could be either one, but all we need to do is look at one of the signs, and then we know all of them are negative. Now the last mystery one, the saddle point, is a mix of concavities, but again, think of this d value that we're calculating as the product of two concavities. If we have a product that's negative, we get that by having a positive and a negative in there, and that is what would mean a mix of concavities, in particular concavity signs. One concave up, one concave down. So in terms of memorization of this, you do need to memorize this formula, and you do need to memorize how the test is once you've used that formula. So you calculate this d value and all the ingredients, the second derivatives. Then you ask yourself, what is the sign of d? And I think of it as the product of two concavities. Positive d, that tells us that the concavities are all the same. Then we dig a bit further and say, well, is it all positive or all negative concavities? If d is negative, we're done, because as soon as we have a negative product, that means we're mixing and matching a positive and negative concavity, and that's a saddle point. With that in mind, we're going to study a few examples and see how we can apply this classification of critical points using the second derivative test, working straight from a formula for a function.